Hello, welcome to another module of this course, Analog Circuits. In the past module, we had seen what are Bode plots. Bode plots, as we have discussed, they are the means to visualize the frequency response of any system, not just an op-amp or not just any analog circuits, for any system. In this module, what we are going to do is we are going to see the details of the frequency response of a typical op-amp and then try to find a means to analyze what should be the frequency response of a typical circuit. So, let us see what is the frequency response. Now, as you know, frequency response is an important aspect of any analog circuit. Now, we have studied the op-amp, and while studying it, we had visualized it as a time domain device, like as if the signals only change in time. But unfortunately, that is not the only analysis that can be done. The reason being, as you know, any signal can be broken up first of all into its frequency components, and any analog circuit like that of an op-amp, they behave differently at different frequencies, and that is why instead of a time domain perspective of the op-amp, it might be more useful to see the frequency domain perspective, like how with variation of frequency the response changes. Now, usually the frequency response of an op-amp, or for that matter any analog device, if we plot the Bode plot of the magnitude, then it will show. So, this is in dB, it will show a variation like this. So, these are the asymptotes, and the overall curve will be something like this, with of course one frequency omega h, where the magnitude falls by 3 dB. Sometimes, depending on the circuit, this response can be slightly modified like this. Here we have two 3 dB frequencies, whereas here we had only one 3 dB frequency. Here actually we have two 3 dB frequencies. So, we call that lower 3 dB frequency as the omega L and the upper one as omega H. Now, so these omega L, omega H, they are the 3 dB frequencies. What is the meaning of a 3 dB frequency? 3 dB frequency means that frequency where magnitude of gain becomes half of its mid band or DC value. So, here this A of j omega, when I say that the A of j omega in dB is falling by 3 dB, it means this A of j omega magnitude square is becoming half of its mid band value. Okay. That is why when you take the 20 dB of this or the 10 dB of this, you will find that there is a fall of 3 dB from its DC value or its mid band gain. So, this is the A0 value this is the A0 value. Now, these two cases arise depending on, as I said at the beginning, what kind of circuit you use. Usually the frequency response is of this type, but in some cases, especially where at the input, where the source is being inputted into the circuit, we have a something called a blocking capacitor. If a blocking capacitor is present, then what it does is it does not allow DC components to pass through it, and therefore, there is a dip as the frequency decreases. So, there is only a mid band gain, there is no DC gain, or there is neither a, for very high frequencies also the gain decreases. We saw that either the response can be of this type or of this type, and for this type, usually this type of response, usually a blocking capacitor is present, which does not allow the DC to pass through it. So, first let us try to find a formula for this omega L first. So, for that we will study what we call the low frequency response. So, for low frequency response, the transfer function can be written like of this form. Now, as you can see, when S equal to j omega tends to infinity, the magnitude of h of j omega tends to 1. For S equal to 0, so when S is equal to 0, we have magnitude of h of j omega given by okay. So, now by suitably choosing this omega z's and omega p, we can make the value of this magnitude h of j omega very low. So, what we will get is a response like this. Okay. So, what this equation implies, or what this graph implies, is that for as the frequency increases, there is a stable value of h of j omega magnitude. Let me draw it nicely. So, this equation, the type of graph that we will get is like this. So, this is again h of j omega in dB. This is log of omega, this is 1, and this omega L, sorry, this is 3 dB and omega L is here. So, at omega L, the value decreases by 3 dB from its stable high frequency value. So, this equation we have, so just I want you to convince yourself that this equation will satisfies this kind of response. Okay. Of course, we have to choose our omega z's and omega p's properly, so that we do see this dip that we are seeing. what is interesting is there is only a single omega L here, but here it appears that there are many poles and zeros. So how do we reconcile with the presence of so many poles and zeros this particular graph? Since while discussing Bode plot, we have seen that every 0 will increase the slope by 20 dB and every pole will decrease the slope of this amplitude response by minus 20 degree. So, if that is the case, then how are we getting such a smooth curve? So, to understand this, first of all, for a response like this to happen in any system, we need to have what we call a dominant pole. So, a dominant pole is a pole for this low frequency response case. This, suppose this omega p1 is the dominant pole, then it is at least 4 times greater than the nearest pole or 0. That is what a dominant pole means. So, if such a pole exists, then can we find out a formula for omega L in terms of that dominant pole? Let us see. So, suppose we have a system where there are only 2 poles and 2 zeros. So, H of S is given like this. Okay. So, therefore, modulus of H of j omega whole square is given by now at this omega equal to omega L, we saw that the magnitude square of H of j omega will be half its stable high frequency value. Therefore, we can write this modulus H of j omega square equal to half at omega equal to omega L. Now, from this we get half is equal to omega L whole square plus omega Z1 whole square, omega L whole square plus omega Z2 whole square upon omega L whole plus omega P1 square, omega L square plus omega P2 square, which in turn can be written as now then solving for omega L, what we get is omega L is approximately equal to omega p1 square plus omega p2 square minus 2 omega z1 square minus 2 omega z2 square. Now, here we have neglected 1 upon omega L 4 term, since this omega L is much larger than the rest of the poles and zeros. Now, suppose this omega p1 is the dominant pole, and it is, as I said, at least 4 times greater than the nearest 0 or pole. So, omega p1 we can write it is much greater than omega p2 or omega z1 or omega z2. Then what this implies is this omega L is nearly equal to omega p1, or in other words, the lower cutoff frequency omega L is equal to the dominant pole. So, in this module we covered the concept of the 3 dB frequency and also the low frequency response of an op amp, and what the lower cutoff or lower 3 dB frequency should be in terms of the dominant pole. In the next module we shall be covering the high frequency response, where we will be deriving a similar expression for the upper 3 dB frequency in terms of the dominant pole. Thank you.